there are two cases. This spectral theorem for real symmetric matrices, and there's another one for complex Hermitian matrices. Okay? So, and I'm talking about the complex Hermitian case. So, if you have A star equals to A, that means it's Hermitian. Then you can rewrite A as a unitary times diagonal times unitary, something like this. But there's something additional that I forgot to say. We also proved that eigenvalues of a Hermitian matrix is what? It's real, right? It can't be complex, and it's always a real value. So this diagonal matrix, if you actually write it, so here's U, the diagonal one will have lambda 1, lambda 2 until lambda n is 0 everywhere else, and all of these values will be real. And then you will have U star here. That's what spectral theorem is. But then you might wonder, like, maybe what I want is, I want something more general. I want something, I want to know, so a lot of times mathematicians observe something and they ask the reverse question. It's like, is it true that any matrix that looks like this is Hermitian? And the answer is yes. If you take this, okay, let's say you do this, and this is transpose and complex conjugate. And if you take the transpose and then complex conjugate, here's what happens. So first of all, transpose, when you apply to it, transpose of AB gives you B transpose A transpose. You can check that this is true. So all of these will have things in reverse order. So you get U bar transpose transpose, D transpose U transpose. You still have to do the bar. But transpose of transposes is self, right? And what's the transpose of the diagonal matrix? It's also itself, because there's, I mean, transpose flips these two, but they're both 0, so it doesn't do anything. And then transpose of U will be transpose of U. Right? We can't do much. But then this bar can now be applied to each individual case, and then conjugate of conjugate cancels, so you have U. And then because D, if these are all real, the complex conjugate doesn't do anything, so it's just D. And then this is what we call as the star. So you see that you do get, if A is this, we just proved that A star is equal to A. So it's vice versa. Spectral theorem is really like vice versa. If A is Hermitian, you can write it like this, and anything that can be written like this, you can write it. You know that it's Hermitian. But then mathematicians looked at this and said, well, is there a way to characterize a weaker condition? What if we want to know all the matrices that look like this, but D not necessarily real? Maybe you can allow complex numbers to be here. So if you look at all of the possible things that look like this, where D is not real, it's diagonal but not real matrix, then you observe the following. No longer, if you call this as A, it's no longer true that A star is itself. Instead, A star will go through all the calculations I did, so exactly the same way. So it will look exactly the same for the other ones, but what happens is that it's no longer true that the complex conjugate of D is itself, because it's not real. Right? So A star will look like this, A will look like this. However, mathematicians observed that, if you have this case, then A times A star will be equal to U, D, U star times U times D bar U star. And then being unitary means that these two are inverses of each other, so they cancel. So you have U, D, D bar, U star. On the other hand, you have A star A So you do this times this, and it's exactly the same computation except that you have d bar first and then d. But moreover, diagonal matrices always commute regardless of their shape. Okay? If you have like A, B, 0, 0, C, D, they always commute if all the off-diagonal elements are 0. It's always just AC, BD. So whether you multiply it this way or if you reverse, you get the same multiple. So these two, because they're both diagonal, these two are equal to each other. So mathematicians observed that, oh, in this case you have A star equals to A star A. In other words, the matrix, if it's diagonalizable using unitary matrices, where the eigenvalues don't necessarily have to be real, they figured out that, oh, in that case, you must have a property where the matrix itself commutes with its adjoint. So they wrote this, and then the surprising thing is, once you assume this, you can actually go backwards. We did all the proofs. So we didn't do all the proofs. We only did the case for different eigenvalues, but we kind of get the idea, right? So mathematicians, in fact, proved that if this is true, then it's also true that it can be diagonalized like that. So that's where this normal matrices come from. So you can think of normal matrices as a expanding of the Hermitian. So you have a very small part of matrices that would satisfy A star equal to A. But if you weaken this to just requirement that it commutes with its adjoint, then you call this normal, and anything normal will still be able to be diagonalizable using unitary. The difference is that when it's Hermitian, it has to be real only, whereas normal, D, may have complex eigenvalues.